Do this little weird thing. All right. Happy Tuesday. Welcome to second week. Today we're going to look at section 3.1 and 3.2. Normally I would do 3.1 on Tuesday and then 3.2 on Thursday. 3.1 is super fast though. It really doesn't take very long. It's pretty short. 3.2 is a little bit longer, but I still cannot imagine we still are not going to be here till 7:20, even though this class is going to be a little bit longer than normal because we're not here Thursday. Thursday, I have parent-teacher conferences at the high school. Yes, I'd still rather be here teaching you all, but parent-teacher conferences are pretty important. So that's where I'll be. Oh, hold on. So we're going to get all of 3.1 done, or 3.1 and 3.2 done today. So you will have everything you need to do the homework. Before we get started, I want to remind you that the first lab and the quiz are due tonight. I will start grading them tomorrow. I generally wait until after the due date closes down before I grade them, because on labs, if you didn't like your lab and you wanted to resubmit it, I don't want to grade it and then you be unable to resubmit it if you like noticed, oh no, I didn't do XYZ. So I just don't start grading them until after they're due. And then I will go in and I'll start grading them. So I'll start doing that tomorrow. They should be graded, I don't know, sometime Friday, probably the very latest. And though I have conferences Friday also, but maybe between conferences, who knows? I'll get them graded as quickly as I can. So that's what's going on tonight. Well, I guess I can talk my way through section 3.1. So we're going to talk about measures of center in 3.1. That's really all it's about. It's about means and medians and modes. So it's measures of center. And then 3.2 is going to talk about like the variability of our data and how spread out it is. We're going to learn about standard deviation. We're going to learn about variance and the empirical rule. The empirical rule is something super important. Hopefully, it will be something that you'll all pick up pretty easily. If not, I'm happy to help you. Definitely happy to help you. I'm happy to help you with anything. Please don't hold yourself back from sending me a message asking me a question because you think that it's a dumb question. There's no such thing as dumb questions, and I don't mind answering them. If you're doing homework and you have trouble with 8 problems and you send me 8 messages, that's fine. I'll answer all 8 of them. Even though I've noticed sometimes people will send me 8 messages and I answer all 8 of them, or I answer 7 of them, and then the 8th message says, "Oh, never mind, I figured them all out." But you know, it happens. But I really don't mind. So please don't think that you're annoying me if you send me 5 or 6 messages in a day. You're not annoying me. I want to help you, definitely. Okay, so let's get going. Get my iPad here. My cat is being extra annoying tonight, so I hope that she doesn't decide to like knock my computer off of its stand or anything. She's really kind of a weirdo. All right, let's see if I can get to my next screen. Okay, so starting right in with section 3.1. So when we're talking about measuring the center, we frequently hear the word average. We use that word average all the time. And sometimes we say average, we mean what we call the mean, like average miles per hour, average commute time, average household income, average height of somebody. But sometimes we mean the median, which is a center. Sometimes when we're talking about average house prices, we're actually talking about the median. So average is not really the best word for that. So we're going to be really specific and talk about which average we're using. If I can do this. Okay. So the first one that we're going to use, and probably the one that we're going to use the most, is the arithmetic mean, or we'd call it just the mean. So when we're talking about the population mean, we use this symbol right here. This symbol is the Greek letter mu. And when we take the entire population and we compute the average with the entire population, we use mu, and we use the population mean. So if you think about it, population gets the cool symbols and samples get the boring symbols. So if it's a cool symbol, it's probably population. If it's a boring symbol, it's probably sample. For example, our sample mean We use this right here. We call it X bar. It's just an X with a line over top of it. And this is sample data. They are sample mean. They are calculated exactly the same way. They are just using different symbols. So there's no difference in how you calculate it. It's just the difference in the symbol that you use. So for population, we use mu. For sample, we use X bar. And population mean is a parameter, which means it refers to a population. Sample mean is a statistic. It refers to a sample. Okay, this is really ugly. Don't worry. It's whenever we use this symbol, the summation symbol, this right here, whenever we use that, it looks kind of scary. All it just means is add them all up. That's all that symbol means. It just means add them all up. So you've done this probably 5,000 times in your life to find the average or the mean. You add all of the data values together, then you just divide by how many you have. So if I have 10 things and I want to know their average weight, add all 10 of their weights together, then divide by 10. So generally what we do with our mean is you round to, when you get your mean, you round to one decimal place that is greater than your raw data. So if your raw data is a whole number, you would round to the 10th place. If your raw data is to the 10th place, you'd round to the 100th place. My open math will tell you what they want you to do. So your homework will tell you. But like on your hand-in homework, when you do the hand-in homework that has you calculating mean, you will just round to one decimal place farther than your raw data, unless you're dealing with money. Money would be the exception because we don't generally round money to 3 decimal places. That's just weird. So we always round money to 2 decimal places regardless. So money is its own entity. Questions so far? Are we okay? We good? All right. Okay. So this data that we have here are the travel times in minutes that it takes to get to work for 7 employees of a startup web development company. So first thing we're going to do is we're going to calculate the population mean. So I'm just going to take all of those and add them together. Find a pen. So 23 plus 36 plus 23 plus 18 plus 5 is 26 plus 43. And then I'm going to divide the answer. I'm going to just do this first, add them together first. I have my fancy calculator. You don't need a fancy calculator for this, obviously. So this adds up to 174. Then I'm going to take that 174 and divide it by 7 because there are 7 employees. So we have about 24.9 minutes. So the average time it takes the members of this startup company to get to work, the employees, would be 24.9 minutes. That would be our average or our population mean. So this would be our mu. My mu's are really ugly and they're going to get uglier and uglier the more I write them. But that's what this symbol is. When I write it, it looks kind of like that. So mu equals 24.9 minutes. So I'm going to randomly choose 3 of these. I'm just going to randomly choose three. And I would like each of you to just randomly choose 3 of them. Yes, I know you can do it in your calculator, but I just want you just to grab 3. Just pick 3. And then you're going to add them together and divide by 3. So I'm going to take this one, and this one. Okay. Yep, that one didn't. I tried to do it with my eyes closed. Okay, there we go. So I'm going to do, this one is mine. Okay, and then I divided it by 3 when I was done. So my X bar is 22.3. That's my X bar. So you can either say it out loud or type it in the chat. What did you get for X bar? What is your average for your 3? 26.6. Anyone else want to share their X bar? 23.5. So each one of these is significantly different. And this is what happens when you take samples is you tend to get different values. You tend to get things significantly different. And this is going to come into play when we're doing standard deviation a little bit later. We're going to have to we're going to have to tweak our formula a little bit to account for all the differences in our samples. So yeah, kind of if you get a sample, especially a really small sample, you kind of just have to take it with a grain of salt and say, okay, so it's probably somewhere in the 20s. But look, 26.6, that's quite a bit higher than my average one, the population average. So our ranges there are from 22.3 to 26.6. But those are all samples. Okay, moving on. So now our we have our 10 students. They're in an introductory statistics course, and we're going to treat them as a population. So I would like you to find the average or the mean, find the mu of these 10 students, find their average test score. I will work quietly behind you. Once you've got it, look up and see how you did. How did we do? Did we get there? Should have added all of them up and divided by 10. All right. So let's each take a sample of 4 and calculate. You only have to do it once. Each of us can just do it once. Go ahead and take a sample of 4 of them and find your sample mean. Okay, those are my 4. I'll erase this so you can see. I have an X bar of 81. Did y'all get? 83.5. And that one's quite a bit bigger than the original. Anyone else want to share there? 77.3. Wow, so these are definitely different. I mean, these are small samples, and when you take small samples, it's always like quite a bit different than your population. The bigger sample size will get you closer there. But so far, questions, comments, queries, concerns? Oh, all right, let's move on. Okay, let's talk about median. So the way that when I was learning this, the way that I remembered what median is you think about like on the freeway, you get like a median and it's the center of the highway, the center of the road. So median is exactly that. It's the center. It is the middle of the data set. So the first thing you're going to do when you're finding the median is you're going to arrange your data from the smallest to the largest. Then you find how many observations you have, and you find the exact center observation. You take the middle number. I'll show you what this is going to look like. Once again, we're going to go to whoops, went too far. Once again, we're going to go to our travel times. So the first thing we need to do is you need to list them from smallest to largest. So here we go. And I'm letting you know ahead of time, I am really bad at listing numbers. I tend to forget or miss them or whatever, or list them twice. I'm so bad at this and I don't know why. It seems like such a simple thing, but it is just not. Okay, so I've listed them from smallest to largest. So now that we have them listed from smallest to largest, we're looking for the center number. We're looking for that center number. So I have 7 data values. Therefore, the fourth one, this right here, will be my median. That right there is my median. That's center data value. I'm going to show you in a minute what to do when we have an even number, because I'm sure somebody in their head was like, what if there isn't a center? What if it's an even number? I'll show you that in a minute. Questions on finding the median with an odd number? All right. Okay, so there's a new employee. That new employee, it takes them 70 minutes to get to work. So once again, we're going to put these in order from smallest to largest. So now I have an even number. So the center of my data is in between these two values. So what I have to do is I have to find the average of those two values. So I'm going to add them together and then divide by 2. So just do 23 plus 26 and then divide it by 2. So my median here is 24.5. So median doesn't have any cool symbol. A lot of times we'll just do MED. Median doesn't have any fun symbol. Right, good. Good, 24.5, good. So it's just that center value, just find the average between them. Questions, comments, queries, concerns? Feeling good so far? Alrighty. All right. I will put these in order from smallest to largest, and I would like you to find the median song length. Let's hope I can do this. You may not want to trust me. I'm so bad at this. And I'm already running out of room too. There are 9 songs here. Go ahead and find that median. Kind of made it easy for you. Right. It's right here. So since there are 9 songs, it is the exact center number. There are 4 songs below the median and 4 songs above the median. Questions? Feeling good so far? Feeling groovy? All right. See if we can find the median of the test scores. Once again, I'll put them in order for you, maybe. I almost put 94 before 90. You're already there, Gwen? Look at you, right on top of things. Man, Speed Racer. So smack dab. Uh-oh, what I just did. Smack dab in between those. You must be better at putting them in order than I am. I also got 79.5. Look at y'all. Good job. All right. So our median here is 79.5. That's pretty darn close to the 79 we got before, isn't it? We got for our regular average for our mean, because our mean was 79. 9.5 is not too far from that. There will be some significance to that later on. You'll have there'll be a reason why we like them close. We'll learn that later on. All right, any questions about median before we move on to mode? I do want to let you know we do not have a sample median. There's just one median. You have data, we find the middle of it. So it doesn't get more complicated than that. Okay, before we move on, this right here is basically the later on, but we'll dig even deeper later. So remember we talked about skewed left and skewed right and symmetric. We can tell by comparing the mean and the median to each other, whether it's skewed left, skewed right, or if it's bell-shaped or symmetric. So if our mean, you will need this. I'm going to put a star here. This question will show up in various places. So you will want this information. So tab it or star it or keep track of it in some way. I used to use little post-it notes as tabs on my notes, things that I wanted to jump back to. So this would be a good spot for that. So if it is skewed left, if the data is skewed left, our mean will be less than the median. So it doesn't just mean a slight bit less. Like for example, we had data where my mean was 79 and the median was 79.5. I would probably say that those are pretty close to the same. So it would be pretty much symmetric. We don't deal in absolutes. Remember, as statisticians, we don't deal in absolutes. Therefore, you therefore, if it's really close, we'll just say it's roughly symmetric. You can use one of those adverbs. But if it's a significantly difference, if the mean is significantly smaller than the median, it's skewed left. If the mean is significantly larger than the median, it's skewed right. If they're close to equal, then it's symmetric or bell-shaped or however you want to call it, normal. So this is an important topic, important thing to think about because we need to be able to compare the mean and the median to get the shape of our distribution. Questions, comments, queries, concerns? All right. Does anyone need a moment here or can I move on? We good? Okay. Make sure you holler at me if I move too fast. Okay. Now on this one, I decided to be super kind and put them in order from smallest to largest to begin with because this is a lot of data. This data represents the asking price of homes for sale in Lincoln, Nebraska. So what we're going to do is we're going to find the mean and the median. Actually, I have those. So we didn't really need to find them on the thing. So our mean asking price is 168,320. Our median asking price is 148,700. I didn't mean to have this one on here already, but that's okay. So because our mean is significantly larger than my median, so see these ones are 20,000 apart. Because the mean is significantly larger than my median, we are skewed right. I'm going to show you a histogram so you can see that this is true. So here's the histogram. We can see that we have this tail over here on the right. So this is definitely a right skew. And I love that you can just compare the mean and the median. It makes life a little bit easier because later we're going to be dealing with data that if it's skewed, we can't use our analysis tools and we have to make them normal. So it's nice when you can tell, when you can compare two things and see whether or not it's normal. It's a pretty cool thing. All right. talk about mode. I guess we're not at mode yet. I thought we were at mode. It's okay. Okay. Once again, I'm not going to ask you to find the mean and the median here, especially since all of my data values are not in order. That would be terrible. So I'm going to show you the birth weights, the mean and the median of the birth weights, and we're going to talk about the size, the shape of the distribution. I did not really mean to have this page. This is actually directly from your book. I thought I was going to show you those weights. I must have lost that slide. I apologize. But take a look here. My mean and my median are very close to each other. Both of them are within 7.2 and 7.7. When our mean and our median are really close to each other, when our data is not skewed one way or the other, the mean is a better measure of central tendency. Using the mean is a better idea. I'm going to give you a chart in a couple of minutes that tells you when to use each one. So you don't need to write it down necessarily right now. I'm going to give you a really nice little chart that tells you when to use which measure of center. So you don't need to write it right now. But because this one is mostly symmetric, it's pretty close to bell-shaped, we would use the median. We use the mean, sorry. We use the median when it is skewed. We use the mean when it is normal or bell-shaped. There's sometimes we'll still use the median other times, but but in most cases, if you have to choose, median is better for skewed data and mean is better for symmetric, but we don't deal in absolutes. All right, let's talk about the mode. We almost never use the mode. Very, very rarely do we use the mode. A set of data can have no mode. It could have one mode. It could have lots of modes. Sometimes if it has two, we call it bimodal. And the only reason I really tell you that is because I like saying bimodal. But if you have two of them, two modes, you would say bimodal.
Do you have a question?
Yes.
If you get down into like, hundredths and your decimal points or something like that, would would you does it have to be exactly identical to be the
No,
same
no, no.
mode?
No, I mean we had 79 and 79.5. I would call that symmetric. If it's somewhat close, I mean if I'm using it depends on the data also. Um, like for example, let's go back. Let's go back. Like these right here. Okay. Where ours were between 7.2 and 7.7 on here. Now, if this was 6 and 8, they're definitely not close. But if my data was hundreds apart, let's say I was dealing with numbers from 100 to 800, if I was at my mean and my median were at like 502 and 505, I would call those basically the same. So it really depends on your data. Like here, 7.2 to 7.7, those are super close right in the middle, whereas 6 and 8 are not. But like right here, using this data right here, if I'm at 168,000, that's my mean. If my mean is 168,000, if my median was at 170,000, I probably would still call that symmetric. It just has to do with if they're pretty close, you just call it symmetric. There's not an exact science to it, but these are clearly far apart because they're 20,000 apart. But if they were just a couple of thousand apart, I would probably still call that symmetric. Did I like answer your question without answering your question? Kind of, sort of. Okay. Let's go back. Let's go back to mode. Okay. We use mode a lot when we're dealing with categorical data. So categorical data doesn't have numbers, and so there's no other way to measure it. So what we will do is we will figure out which one has been counted the most. So our example here, the slide that we have next is of vice presidents of the United States. It and where they were born. Now, I don't have Kamala Harris or JD Vance on here because I have a nice, perfectly rectangle thing. I don't want to just add two more boxes over here because that would make it ugly. And I like things pretty. So I'm stopping at Mike Pence. So here I have all of their birthplaces. So what I did was I created a frequency table so that I could see who was born where, who I wanted to see where most vice presidents were born. So our mode here, New York, because most of the more vice presidents were born in New York than anywhere else. So that's the mode, the thing that is counted the most. Now, the only way this would be bimodal is if another state had exactly 8 also. Let's just pretend that Ohio also had 8. This is pretending. Then this would be bimodal. I would have 2 modes because both of those states have the same number and they're both the highest. Sometimes you don't have a mode at all. Sometimes nothing is the highest. Sometimes you have like 8 things that all have the same highest. I would say that that one doesn't have a mode. But if you just have 1 or 2 or maybe 3, then we would can say that it has those are all modes. I probably wouldn't go more than 3. I usually stick to 1 or 2 would be mode, but as we don't deal in absolutes, so I'm not going to be mad at you if you count 3. Questions on mode? Because that's all you really get. Okay, I already said that. Here's our table. This is the table I was telling you about. So with mean, we have a population mean has mu, sample mean has X bar. We use this when the data are quantitative and the frequency is roughly symmetric. So if we have symmetric data and are close to symmetric data and we're using quantitative data, then we will use the mean. For median, if we have quantitative data that is skewed left or right, then we will use median. Mode, we use it for qualitative data, or if we, for some reason, want to know which thing occurs the most. So this kind of tells you the when. Questions, comments, queries, concerns? I believe this is the end of our section 3.1. So if you have any 3.1 questions. This was a pretty low math section. I'm going to give you heavy math in the next section. Kind of like heavy metal, but more mathy. We are in section 3.2 now. If you keep track of that sort of thing, this is section 3.2. We're going to be doing some heavy math. I'm going to show you a fun calculator function. So we're going to be learning something really cool on our fancy schmancies. That's what I call these things, fancy schmancies. The whole generation of high school students that's what they call them. So I can't wait till they start coming through the college and calling them fancy schmancies. So the range of the data is one of the most boring things we do. It is just the largest data value minus the smallest data value. That's it. That was all your excitement on range. Just take the largest data value, subtract the smallest data value. That's your range. That's it. All of the range excitement is over. Okay, we're just going to take our travel times and we're going to find the range. My largest is 43. Uh-oh. My largest is 43. My smallest is 5. Do I have another screen for that? No. I thought I had it on another screen. So I just do 43 minus 5. So my range is 38. There's 38 minutes in travel time between my longest commute and my shortest commute. There you go. That was so exciting. Can hardly contain myself. Me and my sarcasm. All right, let's move on. Okay, this is the scariest looking formula, but it's because it has sigma on it, but don't worry, it's not so bad. Remember that if it has a cool symbol, it is population. In the case of standard deviation, population and samples are going to have different, they're going to have different formulas, just slightly different. So what standard deviation is it tells us how spread out data is. Data that is more spread out is going to have a larger standard deviation. When our data is more grouped around the mean, we will have a smaller standard deviation. Basically, what standard deviation is, this is the simplified version. It tells us the average distance each data value is from the mean. So it's saying I'm averaging all the distances from the mean, and then I'm going to get that standard deviation. So obviously, if I have a lot of data values that are far away from the mean, that average distance is going to be greater. So since distance is always positive, standard deviation is always positive. I'm going to tell you, we are going to be using standard deviation the only unit we won't use standard deviation is chapter 5. Other than chapter 5, oh wait, maybe not chapter 4 either. Other than chapter 4 and 5, every single other chapter, we're going to be using standard deviation. So this sticks with us. We're going to calculate it by hand once or twice. You're going to do it by hand twice in your homework, and then you never have to calculate it by hand again. You'll be able to just use your calculator. So here's how we calculate standard deviation. Yes, we're going to walk through it together. So I'm just going to give you the overview, and then you'll have a list of steps. So you don't need to write it down right now. So what we do is we calculate the mean of our data set. We take each data value, subtract the mean from that data value, then square the result. Take the next data value, subtract the mean, square the result. Do that with each data value. Then all of those squared results, you're going to add them together, then divide by the number of data values you have. After you do that, take the square root of your result, and ta-da, you have a standard deviation. So we're going to do this together. Here we go. So these are those travel times we were talking about we've been using. These are the travel times. Do you guys remember what the average travel time is? I bet I can find it on my calculator. Let me see. Maybe not. I thought I had it right on my thing. Does anyone have that number? It was 24.9. Okay. So 24.9 was our average. So I'm going to put that right up here. Mean equals 24.9. I must have deleted it out of my calculator. 24.9 is our average travel time. So I'm going to take each of these data values and I'm going to subtract it from the mean and then square it. So here's what it's going to look like, or subtract the mean from it and square it. 23 minus 24.9 squared. So I'm just going to put that in my calculator. Parenthesis, here's how, if you're going to put it in your calculator, here's the best way to do it. Do parenthesis, 23 minus 24.9, close your parenthesis, hit the x squared button. Next one, 36 minus 24.9 squared. So once again, parenthesis, 36 minus 20, oh, that's not a 2. 24.9, close your parenthesis, x squared, enter. Thankfully, I already have this next one. I love it when things are repeated. Do 18. I'm so glad this isn't a bigger data set. Okay, got 5. This one's going to be a big number. $396.01. 26 minus 24.9 squared. $1.21. That one's little. Then 43 squared. It almost looks like I intentionally made the box just that size. I just got lucky. 327.61. All right. So I took each of the data values, subtracted the mean, and squared them. Now, next thing we do is we're going to add up all of those squared differences. Going to add all of those numbers up. Added them. I'm just going to put them over here. 902.87. Please confirm if you got the same number I did. Yeah, you did. Okay. We all get there? Now, next thing we want to do is calculate the square root. So I'm going to just take the square root of this value. So if you don't know your calculator, it's the second button, then the x squared button. Second x squared. So I have 5.48. That doesn't seem right. What did I do? Nope, I took the square root twice. Yeah, silly me. Wait, hold on, back up. I messed up. How come it doesn't say, I forgot this part. What's my problem? See, it's been a long day. I have 7 data values. I was like, something's wrong here. That's my problem. Take the 902.87 and divide it by 7. Divide it by the number of data values you have. Man, I have issues. So I took the 902.87, divided it by 7. Now we square root. Forgive me my math mistakes. I apologize. It's another example of your math teacher is human. There we go. That looks more right. Okay, so there we go. Yay! Good. Good job. So the average distance each of our data values is from the mean is about 11.36. 11.356 if you rounded 3 decimal places, yes. Or we would have rounded it to 7. You truncated, that's okay. So about 11.36 minutes is the average distance each of our data values are from the center. Now, this next week, the standard deviation is going to have a lot of really important things. Right now, we're just focused on calculating it. We'll start using it in really important ways next week. But right now, we're just going to be happy that we did all this math and it came through beautifully. Questions on calculating the standard deviation? Other than the Kleist, how dare you? How dare you make math errors? All right, let's move on. Methinks that Gwen is already calculating the standard deviation of the test scores. No? Okay, so I'm just sitting here. So let's have a consensus here. Do we need one more by hand calculating of standard deviation, or do we want to jump straight to learning the calculator function? I'm up for a democracy. We can take a vote here. Do you want to do another calculating by hand, or do you want me to go straight to the calculator function? So do we feel that you could just go back to this example and be okay? If you had to calculate it by yourself, that's really what I'm looking at. If you feel that you can look at this example and be like, yeah, I can use that example to calculate it myself, then we're fine. All right. I'm just going to jump to the calculator function. We're going to use this data set right here, the test scores. Okay. So I'm going to go to I have an emulator right here, my lovely calculator emulator here. So get out your calculator. And it might be a good idea to write down the steps. I mean, we'll be doing this a lot throughout the term, but if you want to write down the steps, the calculator steps, that's probably could be a good idea. So what we're going to do first is we're going to enter the data into a list. So you're going to click on Stat, and then we want the first option of Edit, and you're going to have all these lovely lists here. Yours may or may not have stuff in them. I always have tons of stuff in my lists. Okay, so when you are here and you're L1 right here, click the up arrow so that it's highlighted. So this is what it looks like when it's not highlighted. When you up arrow, it's highlighted like this. Then if you click clear, enter, it will empty your list. Okay, yep. Hit stat. The stat button's right here next to the circle. It's right there. And then hit enter because we want the first option, the edit option. Okay. And once again, arrow up to highlight L1, then hit clear, enter. Do not hit delete. I mean, if you do, it's not that big of a deal, but I can help you get back to having the list that you just deleted. In fact, let me just show you, because inevitably somebody's going to delete your list. So let me just delete it. Let me accidentally delete my list. See, I no longer have an L1. So if you deleted your L1, you click on second delete, and it puts a new list in there, and then I need to name it. So if I do second one, it renames it and then hit enter, and it inserts that list back in there. But just don't hit delete, just hit clear, enter. All right, I'm just going to start entering these in. Just type in the data values, hit enter between each of them, and it'll bring you down to the next line. So I have 90, enter, 71, enter, and so on and so on. So you get all of them in there. I'll give you a second. I highly recommend afterwards taking a look at your numbers and checking them against your list to make sure you didn't typo. Most common error is typoing in your calculator.
I do have a question. If you do make a typo, is there a way to go back and fix one number?
Yeah, you should be able to arrow up.
Mm-hmm.
And like, let's say that this one was supposed to be 75. I can just type over it and fix it.
Oh.
Yeah,
Thank you.
you're welcome. Okay, does anyone need me to stay here? Are we good? Okay. Now we're going to go to the next screen that we need in order to calculate our standard deviation. So I'm going to click on Stat, and then we're going to arrow over to Calc. So arrow over 1, and it'll say Calc right up here on the top in the center. So Stat, arrow over to Calc. We want this first option. This first option, it says it's one variable statistics, or you can say one var stats. That's usually what I call it. So one var stats right here is where we want to go. So our list, we put in which list we used. So you didn't probably notice that there are 6 different lists up there. So we want to put in the list that we used. So we used L1. If you don't currently have L1 in there, you just hit second 1. That gives you L1. If this was L2, you would do second 2. If it was L3, you would do second 3, etc., etc. The frequency list, that's what this is. We're just leaving it blank. Just leaving that blank. And then go down to calculate and hit enter. There's a whole lot of stuff here. I'm not going to tell you what each and everything is right at the moment. We'll come back to the screen later and I'll point out the rest of the things, but there's a lot of stuff here. This top thing right here, this X bar, that's our mean. The calculator always assumes that this is a sample, so it's just going to call this X bar. The second one is the sum of all the numbers. So all of our numbers added up is 790. The third one is something I've never ever used. It is adding up the square of every number. I've never used it. I have no idea why we'd have that. Okay, notice this right here. This is a sigma, just like our standard deviation, This right here is our population standard deviation, which is what we just calculated. So this is important. This one right here is population standard deviation. I will tell you what the other things are later, but those are what's important right now. Our sample mean, or doesn't matter, population mean, sample mean, they're calculated the same way, it doesn't matter. This sigma right here is our standard deviation. So our sigma, I'm going to write it on my screen before we go away. My sigmas are really ugly, by the way. You'll see. They're very, very ugly. I'm going to try it again. Sigma is 9.82. I'm just going to write it going out 2 decimal places. It doesn't matter. So that would be my standard deviation. So my standard deviation here is 9.82. So every test score, the average distance, the test score are from the mean is about 9.82%. Questions? Okay, let's move on. So sample standard deviation. So sample standard deviation is almost the same as regular standard deviation as population. There's a little bit of difference here. Number one, as I said before, samples don't get fancy symbols. They get a lowercase s. So sample standard deviation uses a lowercase s. The other difference is instead of dividing by the number of data values we have, we divide by n minus 1. So I'm sure you noticed, because I kept bringing it up, when we were doing sample mean, our means, our sample means were very different than our actual mean, our population mean. Our values were very different. Because of this, we have to kind of account for that difference in our sample standard deviation. So because of the variability that there is in sample values, we are kind of like erring on the side of caution and dividing by n minus 1 instead of n. So if I had 10 data values, I'm going to divide by 9. If I had 12 data values, I'm going to divide by 11. So you always divide by 1 less than the number of data values you have when it's a sample.
Why doesn't that just make it too artificially big?
And it's just kind of the way they've decided to do it. So I'm going to pop back over here. This SX right here, this is my sample standard deviation. It's not significantly bigger. And it's 10.3 compared to 9.8. I mean, it's about 0.5 bigger, but it just has to account for the variability. And I think there's even deeper meaning there because I've done a lot of research on it, and some of the explanations just don't make sense. So I just kind of ignore those. The only one that made any sense was we're just trying to account for the variability in samples.
Okay.
So erring on the side of caution, basically. That was a good question, though. So just remember when you're doing sample standard deviation, you're dividing by n minus 1 instead of by n. So let's take a look at the next screen here. All right. So we have our random sample from travel times right here. And I'm just going to do these by hand because there's only 3 of them. So I'm going to find the average of these 3 values. So my sample mean is 22.33. So I'm going to calculate the sample standard deviation. I'm going to do 5 minus 22.33 squared plus 26 minus 22.33 squared plus 36 minus 22.33 squared. I'm going to do that first. I'm going to do it all at once in my calculator using parentheses just like it looks. Except for the fact that I missed a parenthesis. Figures, okay. Okay, so adding all these up, I got 500.67. So I'm going to take this 500.67, divide by 2. Remember, we're dividing by 1 minus, or the number of data values minus 1. So I got 250.33. Now we're going to take the square root. $15.8. Trying to remember, what was our standard deviation previously? 11.36 was our standard deviation previously. So this one's significantly bigger. But part of that is because, I mean, I have one of the larger data values. And also we only use 3. If we're using a bigger sample, it's not going to make as big of a difference. This is a really small sample. But this would be our sample standard deviation. So we just use a little s. Remember, they don't get a fancy. They don't get fancy. Questions about that?
Yeah, so while you were doing that, I did it on my calculator and I'm looking for the uppercase S with an X for my answer.
Yes.
Okay.
Because we have SX for sample standard deviation and then sigma X for population standard deviation.
Okay, thanks.
You're welcome. Now, doing your regular homework, doing your regular MyOpenMath homework, just use your calculator. You will have a hand-in homework that requires you to do it by hand, but the data sets aren't super large, so it shouldn't be terrible. I'm going to jump to that after we, at the end, I'm going to jump to it really quick because there's sometimes some misconceptions and I want to clear those up before anybody jumps into the hand-in homework. So I'm going to try to help you with that a little bit. All right. So, I don't know why we're doing this. Second here. I think that was not even supposed to be there. I just jumped past it. I don't know why that was there. All right. So we're going to kind of look at a couple of standard deviations and talk about what it means. Because there is a question in your homework, I think talks about standard deviations of like investment firms or something like that. So I'm going to talk about comparing standard deviations and how it can be helpful. So right here we have wait times at Wendy's and at McDonald's. I'm assuming it's drive-through, but that's just me with an assumption. I have no idea if that's really what it is, but in my brain it's a drive-through. So this is just raw data. It's not very meaningful because it's just a bunch of raw data. So what I did was I calculated the standard deviation of each of these values. So I have that Wendy's sample standard deviation, because it was just a sample of the data, is 0.738. McDonald's sample standard deviation is 1.265. So this doesn't tell us anything about who has longer wait times. It just tells me that Wendy's wait times are more consistent and more predictable because the standard deviation is smaller. They're kind of more reliable on their times. Their wait times are not spread out as much. McDonald's wait times are spread out quite a bit. So if you were looking at, hey, which one can I as most reliable, or maybe I'm like trying to predict, I only have a few minutes left of my lunch hour, which one am I, can I guess that Wendy's is probably only going to take 2 minutes and McDonald's could be anywhere from minute and a half to 5 minutes? I don't know. So Wendy's is just more predictable. It's more reliable. So for example, if I was going to go to an investment group that had a standard deviation, a smaller standard deviation for their the return on investment, I probably would go there because they have more consistency. That's all it means, is that they are more consistent with their times. All right. Okay, we're going to talk about variance. I have never, ever, ever used variance in any meaningful way. Let's say it one more time. I've never used variance in any meaningful way. The only time I ever have to calculate variance is when someone says, hey, calculate the variance. I've never used it in anything meaningful. However, I know that your homework will ask you for variance. So let me tell you, all that variance is before you take the square root in the calculation of your standard deviation, that's the number. So it is standard deviation squared. That's all it is. It is the square of the standard deviation. That's the variance. That's it. I don't know what it's useful for. I'm sure there's something, but I've never used it. I don't know anybody who's ever used it. So there you go. Variance is the square of the standard deviation. All right. Okay. Now, this next piece, we're going to talk about the empirical rule. This is, we're actually, we're still going to get done before 7 o'clock. I'm guessing there's another 10 or 15 minutes left of me talking. I apologize for talking so long, but hey, you're free Thursday night. So, empirical rule is something that's going to come up quite a bit. And there's two camps of people. There's camps of people that totally get it and are like, "Oh yeah, this is great. I know how to use it. I'm doing great." And then there's the camps of people that for some reason they just can't wrap their brain around it. If you end up being in the second camp where you just can't wrap your brain around it, send me messages like crazy if you need to. I'm completely okay with it. And also keep drawing the picture. That's all I got to say. All right. So with the empirical rule, what the empirical rule tells us, about 68% of all data is within one standard deviation of the mean. That means if I take the standard deviation and I add it to the mean and I get that value, then I take the standard deviation and I subtract it from the mean and I get that value. Within those two values is going to be 68% of my data. And I'm going to draw a picture and make it hopefully much more clear. So now, if I take the standard deviation and I multiply it by 2, then I add that number to the mean. Then I take that 2 standard deviations and I subtract it from the mean. I'm going to have another range of values. 95% of my data is going to lie within 2 standard deviations of the mean. Okay, moving on. Maybe. This drawing right here, you might want to print it out and keep it with you. What is probably a really good idea, if you have a dry erase marker and a sleeve, like for like a paper sleeve, what are those protectors, sheet protectors? You can keep writing with a dry erase marker on it. You are going to draw on these diagrams 50 times in this class. So I highly recommend if you have a sheet protector, you can print this off and slide it in the sheet protector and use your dry erase marker and write on it. It's going to happen a lot and that'll be helpful. Okay, so I'm going to once again show you. I'm going to use a highlighter. 68% of your data is within one standard deviation of the mean. So 68% of your data is in here. So I have 34% over here and 34% over here. This is the mean, right? This is the mean right here. That's the mean. So within that one standard deviation is 68% of our data. Then I have 95% of my data. Let me get a different color because I can. So between here, this is 98% of my data. I still have the 34 and the 34 right there, but now I have another 13.5% in each of those spots. Okay. Now this is going to come up a lot, but everything outside of these 2 standard deviations, so this area here, everything outside of this, anything not in that square is an outlier. Anything not in there is considered unusual and it's considered an outlier. Okay. This is going to come up a lot. I think next week we talk more about outliers. So I'm just kind of planting the seeds right now. And we're really going to dig into outliers next week. But I'm just kind of planting that seed. 99.7% of our data is within 3 standard deviations of the mean. So, whoops. So here, all the way here, 99.7 of my percent of my data lies within 3 standard deviations of the mean. And this is really ugly, and so I'm going to erase it because I like pretty things, and that's not looking pretty. All right. So within 3 standard deviations of the mean, that's 99.7% of our data. And you can see right here all of these percents in each of these areas. So like I 2.35, whoops, 2.35% here and here. There's 0.15% in each of these teeny tiny little tails outside the 3 standard deviations. Each of these is sectioned off. I think I have questions about it that can help you make sense of this in a minute. But this diagram right here is super helpful, and you're going to be writing all over it. So you can either just keep drawing it or have a bunch of copies printed or do the thing with the sleeve protector and the dry erase marker because it's so helpful. And it will be super helpful on your test as well. That's going to be coming up in a couple of weeks. So I would highly recommend doing that. Any questions on this before I move on and give you some examples? Okay. And once again, so these are estimates. When you're doing your hand-in homework that's coming up, when you're going to do the hand-in homework, if you go and get some help from the tutoring center, make sure you tell them that you're using the empirical rule because we have a calculator function that gives you more exact answers, but we're looking for the estimates from the empirical rule on your hand-in homework. So make sure if you do go to the tutoring center that you tell them that you want the empirical rule answers and not the fancy schmancy calculator answers. Okay. Here's my example. So this data right here represents the serum HDL cholesterol of 54 female patients of a family doctor. Oh, don't worry, you don't have to put these in your calculator, but this is just my raw data. So I'm going to give you the population mean and standard deviation. We're going to draw a histogram, and then we're going to look at the empirical rule and answer some questions. Here's my histogram. So my mean is 57.4. The standard deviation is 11.7. And it is, I mean, there might be a slight skew, but it's roughly symmetric. I can draw a nice bell over here. That was ugly. I can draw a bell over it, and it's close enough. We're going to call that symmetric. It's close enough. Once again, we don't deal in absolutes. If it's close enough, we call it close enough. This is the tough thing between stats and like other math classes. Other math classes are like super precise, but with stats, we're like, close enough. All right. So what we're going to do is we're going to determine the percentage of all patients that have serum HDL within 3 standard deviations according to the empirical rule, which we already know that, but we're going to take a look at a diagram. Here's my empirical rule diagram. What I did was I took the mean, which is right here. This is the mean. We put that right in the middle of the diagram. I added 11.7, which is the standard deviation, and I got this right here. Then to the 69.1, I added 11.7 again, and I got this value right here. Now I'm 2 standard deviations away from the mean. Then I added 11.7 again, and I got right here. Now we are 3 standard deviations away from the mean to the right. Next, over here, I subtracted 11.7. I'm now 1 standard deviation below the mean. Subtracted 11.7. That's where I got that number. I'm 2 standard deviations below the mean. And once again, subtracted again. That's how I get those numbers. I just added and subtracted 11.7 to get 1 standard deviation out, 2 standard deviations out, and then 3. So this is just my empirical rule diagram with it labeled with specific data values. So what this question right here asks me, what percentage of all patients have serum HDL between 34 and 69.1? Your homework's going to have questions like this. So what I'm going to do, I'm going to use my highlighter. So 34 is right down here. So I'm going to shade in all of the areas that are between 34 and 69.1. So those are all of the areas between the 34 and the 69.1. You don't have to shade them in if you want. I'm just trying to like make you be able to see what we're looking at. So in order to find what percent are between those two values, I add 34 plus 34 plus 13.5 because those are the areas in between those two values. And I know I could do this in my head, but I'm not going to do this in my head. Uh-oh. It would have been so much better if I would have been on the screen that I could do that with. So this is 81.5%. So about 81.5% have a serum HDL cholesterol between 34 and 69.1, according to the empirical rule. Questions about what I did there? Okay. Now what I'm going to do is I'm going to go back to our data, our raw data, and I'm going to count how many are between those two, and we're going to see how close we are. So let's go back. 34 and 69.1 are the numbers I'm looking for. 34 and 69.1. Just I'm missing that one. Guess I can do it that way. Looks like all the rest of these. Okay, out of these 54, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 that are not. So 45 out of 54. So that number, I'm going to go back to my other screen. The actual, put it in a different color because I can. The actual is 83.3. That's really not terribly different. I probably would have been upset if I would have gotten like 88 or something, but 83.3 and 81.5 are only a couple percent apart. Considering that we're using this general rule to for our data, that's pretty good. And especially since if we look back at the histogram, it was only mostly symmetric. I mean, it looks like there was probably a slight skew there, so that can kind of account for that difference. But I'm not mad. I'm not mad about that little difference. Okay, so I think that's actually all I have. Look at us, 6:47. That's all I have right here. I'm going to jump to the hand-in homework, but before I do that, I want any questions that you have. Anyone? Okay, maybe they will come up while I'm jumping to the hand-in homework. I'm going to go to my open math. This is like the way my interface looks. Let me see where we are. Week 2, I'm going to go to the hand-in homework and I'm going to open this up and I'm going to talk about it just for a minute here, if I can find it. There it is. Okay. Maybe. There we go. Okay. So, I want you to calculate your means by hand. So you're just going to answer a question right here that asks why we think HUD uses the median instead of the mean. You go ahead and just answer that one. This number 2, you aren't taking a sample. This is a sample. So these 5 data values represent a sample. So just add them up and divide by 5 and you're good there. And same population, add them up and divide by 5 and you're good there. I want to see your work. So please show me the work there. And this is our cell phone bills. Okay, I don't really care. This isn't anything I really need to talk about. This I do need to talk about the standard deviation. Once again, this is our sample. And this will be the last time that you have to find standard deviation by hand. I want you to show me your work. Yes, you can do your calculations in the calculator, but I want to see the setup. I want to see whatever the mean is. I'm going to pretend the mean is 25. It's not, but I want to pretend it is. I want to see 8 minus 25 squared plus 42 minus 25 squared, et cetera, et cetera. I want to see your whole setup. But yes, you can just put it in your calculator. Um, and you can also just, you don't have to show me you calculating the mean. You can just write down X bar equals. You can just show me the mean. So you don't have to hand calculate the mean there. But I do want you to hand calculate the standard deviation. That'll be the last time I ask you to do that. And I'm going to scroll down here. So these here on number 6, I want you to use the empirical rule. So as I said before, use the empirical rule. If you need to draw it, draw it. If you need to draw the picture, go ahead and draw the picture. You have plenty of room down here. You can just draw the picture right there or use your own picture. I don't expect work here. You can just write the answers. That's fine. Um, but if you go to the tutoring center, make sure you tell them you're supposed to use the empirical rule, not the fancy calculator functions. And that's really all I have there. Does anybody have questions on the hand-in homework? So I am 100% okay with if you don't have a printer, you don't have to write every single word here. I mean, that's a lot. You can just write number 1 and then answer the question. And number 2, show me your data and then, calculate it. You don't have to write every single word. Just make sure that it's clear which question you're answering if you're just writing it out. I also have had people type the work and everything directly onto the Word document. That's fine as well, but it is tedious. Typing in all of the stuff on standard deviation is pretty tedious. I don't recommend it, but if you do it, you do it. That's fine. Right. That's all I have for you today, unless anyone has any questions and go ahead and give me any questions for while we're being recorded, and then I will turn it off afterwards and you can ask me any questions for when we're not being recorded.
Kind of off topic question, but for like the lab to turn in, so I downloaded the Excel, did it all on there, and then do we just upload it by choosing a file?
Yes.
And okay,
Yes.
perfect. Thank
Yeah,
you.
just upload by choosing a file. Yeah, that's and if you're some people are like, I don't know if this really worked correctly, you can also click on the show work button and upload it. I don't care if you upload it twice, it doesn't matter to me. But and
And
if
you said those will show a 0 at first, right?
yes, they're going to
Okay.
show a 0. What I have it set right now, I have it set so that the 0 won't count in your grade. After I
Mm-hmm.
grade them, then I will enable it to show in the grade. So
Okay.
it shouldn't reduce your grade. However, the quizzes will, because some of the things need to be manually graded, the quizzes will reduce your grade a little bit until I grade them. Just
Okay.
FYI.
Perfect.
Uh-huh.
Thank you.
You're welcome. The upcoming test. So the test is still a couple of weeks away. I'm going to give you a lot more information as we get closer. I believe the week 3 has wait, it's not even week 3. Let me see, I'm trying to remember what the first test goes through chapter 4. So we still have a little bit of time. Let me take a look at the test dates. I will give you a lot more information when we get closer. Let me see. Test dates. Yeah, we still have until April 22nd. So I'm going to give you a lot more specifics. I will say you can use your notes. You can use any notes that you generated. So if you print off the PowerPoints and have been writing on the PowerPoints, you can use those. You can't use the book. You can't use somebody else's notes, but you can use any notes you've generated. If that makes sense. And you can use your calculator because I would never, this is important. You can use this. And so I'll give you more information as we go. And I'm also going to do a practice test when we get closer so that we can make sure that the software works on your computer. So there'll be a practice test. It'll be worth a few extra credit points. All right, anything else for while we're being recorded? Okay, I'm going to turn off the recording.